So, we are in second year lab, optics lab of Department of Physics, IIT Kharagpur. So, today I will demonstrate this bi-prism experiment for measuring the wavelength of a monochromatic light. So, this is the setup for bi-prism experiment. Okay. So, here this is the source. Okay. So, in front of source, this is the basically pinhole. Okay. So, light is coming through a hole and that light is falling on a slit. So, actually for our experiment the source is this slit source. Okay. So, we will take this one as a our source position. Okay. So, we have it is fixed on the optical table. So, there is a marker here. So, one can note down the position of the slit source. So, I can see the reading, it is 55 millimeter, 5.5 centimeter. So, one can note down this reading. Now, this is basically bi-prism. You can see this bi-prism here, this edge, it is there is a edge of bi-prism, as I showed you, there is a edge of the bi-prism. Okay. So, this edge you can see here, this edge you can see here. Okay. So, it's like this, Okay. So, this the bi-prism we have placed in front of the slit source. This also is what is the position of this bi-prism that one can note down from here. So, I can see the reading is around 103 millimeter, 103 millimeter. So, that means this bi-prism and the slit, this position if you note down, so you will know the what is the distance between bi-prism and the slit. Okay. So, now theory is telling that this light source, one source is, so one source is, okay, light from this source is falling on the bi-prism. Now, there will be two virtual image at this position. So, that we cannot see, virtual image I cannot see. Okay. So, now say suppose this I will show you later on. So, suppose this I have fixed these two position and virtual image are formed. Okay. Two image are formed. Now, light is coming and there will be interference, actually you can see here. So, from this source light is coming in this region and from this source light is coming in this region. So, overlapping region is this part. So, I will see the fringe, this type of fringe for due to the interference. Okay. So, this is the screen. Now, you have source, now you have bi-prism, I have showed you. Now, this is the screen. This screen is basically eyepiece. So, this is the eyepiece. Okay. This is the eyepiece. Now, on the plane of the crosswire, this image fringe are formed. This fringe you can see, this is the fringe. Okay. Dark bright, this is the fringe here you can see. Okay. So, fringe are formed. Now, using this micrometer here, there is a micrometer scale. So, this is basically we can say this is a screw gauge principle. You have linear scale and circular scale. You know, in experimental physics 1 I have showed you that how to calculate the list count and how to take reading. So, this is the micrometers scale is a screw gauge principle. So, we tell the micrometer. So, from here this crosswire, you can shift the position of the crosswire, just changing the rotating this micrometer, and you, so crosswire I will fix at the fringe number 1, and then I will take reading, and then I will shift 2, 3, 4, 5, or as I told 6th one, 11th one, 16th one. Okay. So, so you can take reading of the fringe. Now, how to calculate the fringe width, that I told you. Okay. So, this I showed you a ready-made. I have done it just to show you this fringe is formed is on eyepiece, that micrometer is attached with that one. Okay. And we can measure the fringe width. Okay. So, principle is simple. Just we have slit source, bi-prism is placed, and then we are getting fringe, that we put this fringe on the eyepiece, eyepiece. So, why we put on eyepiece? I could put this, so I could put this screen here, but I will not be able to see the fringe width, fringe separately, because their separation is so small. With bare eye it is difficult to see. Okay, on the screen it is difficult to see. So, eyepiece is basically magnify the image and we can see. So, that is what happened. It's a magnified image basically we are seeing here. So, now I will disturb the setup, and step by step I will show how to do this experiment, how to set this experiment in this hall. Okay. So, that time I will not use camera, just I will show the procedure. So, here there is a crosswire, I can move this here, this black one is crosswire. If I am moving the crosswire. Okay. This crosswire is moving, but I think it's difficult to see. Yes, crosswire is moving. Anyway, so I think it's disturbed now. I think crosswire is this position. So, that position of the crosswire one can move using this micrometer. Okay, and set at different bright one and take the reading and shift to the other, from left to right and right to left. Okay. So, as I mentioned in previous class. So, let me disturb the setup. Okay, because I before disturbing I showed you, because this optical arrangement, it takes time to get this fringe. So, I will not spend that much time to get the fringe again, but I will show you the procedure step by step. So, you can see this is the just here we have used sodium source. So, here this one pinhole, this is a screen. The reason is that I want to obstacle other light to come and fall on this. Only light will come from this hole and fall on the slit. Okay. So, here you can see this is the slit. Okay. I can increase and decrease the slit width. Now, I am opening. So, slit width you can control, okay. So, generally we keep slit width is very small, yes, at this end. So, then I have to put this slit, marker is this side. So, I will put this slit as close to the hole, okay. So, it was at I think I will keep at the same position, it was at 55 millimeter. Okay. So, I will fix it, there is a screw here, I fixed it. Okay. Okay. So then I will see the, yes, light is coming, and I can adjust the width of this light is closed. Now reasonable light is coming, fine. So now this is my slit source, okay. This the, now I will place bi-prism. I will place bi-prism as a bi-prism. You can let's, whether you can see the edge of this bi-prism, okay. This is the edge of the bi-prism. So this bi-prism fixed on a holder. So in this holder you can rotate the bi-prism on its plane, as well as also you can rotate this bi-prism. You can rotate bi-prism this way also, okay. So and also you can shift x, this translational motion, it has this, and on the on this you can change the position, okay. So now this bi-prism, now whether this, which face should be towards the slit, it's the plane face, is the plane surface, and this one. So any one it can be, you can put any one towards the source. So generally we put this plane surface towards the source, okay, but it can be in opposite way also, there should not be any problem. So now I will put here, okay, now I will put here. So it was at this place, you know, it was at this place. I think I think I will, marker is this other side, so marker is other side, yes. So its position was 103, as I told you, its position was 103, I kept at the same position, okay. Now this also we have to note down, and here you can see this for this position of this, uh, bi-prism. So these virtual image are formed. Now using the convex lens, as I told, that you can get the real image. Now that getting the real image, whether, let me see whether I can show you on the screen, okay. So this is the convex lens, its focal length is around 10, okay. So I will put this one, okay. So for this position of the lens, this bi-prism and the source, virtual image are formed, supposed to form this virtual image. Now if I use the lens, then we will get this real image on the screen. That screen can be your micrometer, that eyepiece, or I will use here this screen here, okay, this white screen, okay. So if I keep this one more than this distance between the source and the screen, if it is greater than 4 f, then we will get the image, real image on the screen for two position of the lens. So let us try whether we can see the I think, yes, it's I think I will take this marker is this side, I will take, yes. So let me see whether we can, yes, you can check, you are getting the image, real image is not equal intensity, okay. So to get the equal intensity, so generally you have to move this other way, move this. Yes, it's a more or less equal intensity of these two image. Okay, so slightly you can make it sharper. So this is the real image, two image you are getting. Okay, because there are two virtual source, okay. So this is for one position, you note down this position from this position of the lens, you note down. So this will be u and this will be v, and this also I have to note down the position of the screen. Okay, so now you try to find out the second position of the lens. So it's a very small image you will get, but yes, it is there, but it's difficult to see, difficult to see the two, but it is there, I can see. It is there, I can see. Here two are there. Now difficulties is that this, when image was bigger for first position, we are able to see on the screen, but for the second position it is so small, it's difficult to see. Okay, but we can see. Okay, so that's why we use the eyepiece. This, instead of the screen, we use the eyepiece. So it will magnify the image, and we can see there on the eyepiece. Okay, so actually I will take away this screen. I will put eyepiece. Okay, I will put eyepiece. Okay, now through eyepiece I will see, I will try to see. So lens is there for two position, yes. So basically for two position, okay, I will see the image on the eyepiece slightly, I think it's I have to make it this way. Okay, so through eyepiece I will see the image, and I have to get the image on the eyepiece. Okay, but that light, I think it's the creating problem to see this. Yes, so actually you have to find out two position. Actually one position is near about this, and that skin, I can see without bare eye, I can see. Okay, so fixed the eyepiece position, it's a greater than, this distance should be greater than 4D, 4F. Okay, so for this position, you find out that two position of the lens, and for each position note down this position of the lens, and then as I told you that this for measuring D1 D2, you have to, for measuring D1 D2. Okay, so eyepiece first position, this is the first position, say, and this lens for position 1 note down, for lens for these two. Okay, for lens position, we don't need to note down, because here image you will see on the eyepiece. Okay, so basically just for lens 1 and for lens 2, okay, left to right and right to left. So two image you will see as I showed you on the screen. So here also you will see these two image. Now it's in, you will see in magnified way. So crosswire easily you can set for one image, and then, or left one, and then crosswire take the reading of from micrometer, So move to the towards right, take the reading again, and again go further and come back from right to left, take the second one, and then come back to the first one. Okay, so take again reading. So that's what meaning of left to right and right to left. Okay, so you will get the value of d1 and d2, right? So it is difficult to show, through the micrometer, so that's why I showed you from here. Okay, so again I will show you on the screen. Okay, so I think it's just take position. Yes, anyway, keep it and take. Yes, so these the two image for second position. Okay, so this for a particular position of eyepiece, means the screen, it will be replaced by eyepiece when you are taking the reading, but here just to show you I am showing. So I will take the second position of the of the uh, of the screen or eyepiece, then again repeat the experiment. Yes, nicely I am getting. Okay, nicely I am getting image, so I can make it equally, yes, equally bright. Okay, okay, for second position also you will get, but as I told, it's very difficult to resolve them. Oh, now here you can resolve, for higher distance you can resolve, but intensity are not equal, so I can try to make it equal. Okay, so from the using the this eyepiece, you can find out the d1 and d2 for 2 3 position of the screen. Okay, now you now distance of the virtual image s1 and s2 is measured. So no way you can disturb this position of the slit and the position of the bi-prism. Okay, because source distance is defined. Okay, two coherent source distance is defined. Now I will remove the lens. Okay, so these interference fringes are formed. So that interference fringe I should be able to see on the screen. But problem is the fringe width are so small. It is even very small than the source distance. Okay, to virtual source distance is very small. Okay, so that fringe I cannot resolve on this screen. Okay, I have to use the micrometer because it shows the magnified fringe. Okay, so in micrometer I have to use micrometer. On this screen I cannot show. Okay, I cannot show, so I have to use micrometer basically. Okay, so I will use micrometer. So again, just through micrometers you have to find out the fringe. Okay, so as I showed you already through camera that how fringe is formed, and this just uh, here this screw gauge, this circular and linear scales are there, and I am rotating this one, means crosswire is moving, so fringe are formed. Okay, so this crosswire is set, say, on this fringe. Now I will take reading of the micrometer. Now I will shift, I will put on the second one or third one, fourth one. For each time you take reading, or as I mentioned, first one I will take, and then I will take the sixth one. Okay, sixth one, then I will take the 11th one, So it will depend on that how many fringe you are getting. So in this case I saw we are getting very few fringes, not much. So in this case we'll take reading of fringe 1, 2, 3, 4, 5. So all we'll take, and then we'll take the difference of 1 to say 5, 2 to 1 to 6, 2 to 7, 3 to 8. So this way also one can calculate. Okay. So for so fringe, interesting things is that fringe width it will depend on, it's a d by lambda. So this d is fixed now. Okay, this source distance is fixed now. Now fringe width you can increase or decrease just changing this capital D, means slit position is fixed. Now changing the screen position, okay, means the eyepiece position, you can change this distance. If for higher distance beta, that fringe width will be higher. For smaller distance this will be lower. Also you can change this d to change the fringe width. So if d is smaller, fringe width will be higher. If d is higher, small d, if it is higher, so fringe width will be lower. Okay, so that's why one has to think that this fringe, to get the fringe also one has to think this field of view of the micrometer, how big it is, and there if fringe width is very high, so then you will get very few fringe only. Okay, but measurement accuracy will be higher, but you will get few fringe. If fringe width are not in medium, fringe width are medium, then you will get more number of fringe on the field of view. Then you can take more reading on larger number of the fringe. Okay, so that one has to adjust. So just take reading as I mentioned here for on the table. Okay, on the table. So for d1, d2, d3 position, so basically this changing these 3 position, for each one you take the reading from the micrometer. Okay, setting this fringe 1 from the left. You see, nothing to just your reference, you are taking one this fringe from the left is a 1, then next one will be 2, 3, 4, 5, because all are equidistant, so there is no problem. So which one you are taking as 1. Okay, so for a particular position of this one, you do this measurement when you are moving left to right, and again go back from right to left, take reading, take average, and your final. For second position, again fringe width will change, then d2 position, d2 repeat for d3 repeat the experiment. Okay, and find out from calculation how to find out, that already I have told you, and you can then calculate the wavelength of this. Okay, so here one thing I just would like to tell you, that I want to demonstrate you. You see this this d, as I told, this d source distance, it depends why we should not disturb the position between the slit and the bi-prism. Once we fixed and measured the small d, we should not disturb it. Why? Because this small d, it depends on the on the distance between the slit and bi-prism. Okay. If distance of the slit and bi-prism, if it increase, so that d value will be the red one, you can see the d value will increase. Okay, d value, that separation will increase. Okay, if this distance is smaller, okay, then separation, this d will be smaller. So let me demonstrate it whether this phenomena we can see on the screen or not. Let me try. I don't know, I have not seen earlier. So okay, so see the, for seeing the image, actually I have to use this one for this. Now this so whatever the separation we are seeing for first position of lens, so if I increase the distance, so as I told, distance between the slit and this one, so this virtual image, that it should increase, distance small d, that should increase. So I am expecting here also the separation will increase, right? Separation will increase. So let me increase the distance of the bi-prism from the okay, you see it's increasing, separation is increasing, you see separation is increasing. Okay, separation is increasing. I am increasing the distance of the bi-prism from the yes, from for this one. So I have to find out suitable to make it more sharp. Yes, more sharp. Yes. Okay. So separation, I am decreasing now the separation. Yes. Okay. So this separation is decreasing. Now increasing the separation between the slit and bi-prism. So virtual image, that distance S1 S2 will increase. So here also this whatever image image of that virtual image is formed, real image, so their separation also should increase, and it is happening, it's increasing, it's increasing. So that's why in this figure I have shown. Okay, when source, this is the bi-prism, when source is here, so virtual image, this is the separation. When source is here, okay, or source is here, but I change the bi-prism distance. Okay, so whatever, so now distance between the source and bi-prism is this, so the virtual source will be here, so now this d value is higher, so that's what is happened here. Okay, so so that distance, this is defined, distance between the virtual image and okay, which are the coherent source formed by the bi-prism. So their separation, it depends on the distance between the source and the bi-prism, and you have to find out suitable source distance, means this distance between the virtual source, because fringe width also depends on d. If the d is, if it is very small, then beta will be very high. So in the eyepiece you may not see the more number of fringes, so one has to optimize. Okay, so fringe width is controlled by d, small d and capital D. So small d and is controlled by the separation of these two. Okay, and capital D of the, of course, this position of the screen, you can see. Okay, so I think that is what the Bi-prism experiment, and it's a very nice experiment, and one can calculate the wavelength of this of the light. In this case, we have used sodium light. It's the monochromatic light basically. It's not strictly monochromatic, but there are very close two lines are there, D1, D2 lines, but we take ordinarily we cannot resolve them. We can consider as a one light of 58 5893 on the average 93 angstrom. Okay, so so one can find out this using very accurately. Okay, so I think I will stop here. We'll continue next class for other experiment. Thank you for your attention.